There are several styles out there to include lithium chloride dew point sensors and psychrometers, but we will only provide a how it works tutorial for a device called the chilled mirror dew point temperature sensor. Basically, you have a contraption like the one shown here, placed in a location where the humidity level is to be measured. There is a light source, which directly shines some light onto the upper photocell. The same light source also reflects light off a mirror and onto the lower photocell. A thermoelectric cooling unit will operate in a way to cool down the surface of a mirror. Once the temperature of the mirror reaches the dew point temperature of the air, moisture will begin to condense out of the air and onto the surface of the mirror. When this happens, the light that was being perfectly reflected from the light source and onto the lower photocell will become a bit scattered. The comparator will compare the amount of light coming directly from the light source and hitting the upper photocell to the amount of light being reflected into the lower photocell. When deviation occurs, that is an indication that moisture has become present on the mirror and thus less light is getting to the bottom photocell. At that moment, such deviation is detected in the comparator. The surface temperature of the mirror will be detected, and that will be reported as the dew point temperature of the air. Returning to the psychrometric chart one last time, there is also this property called enthalpy. That is the total heat or energy content of the air. It takes into account the dry bulb temperature of the air as well as how much moisture is in the air. There are times when it is important to measure such a value, in particular for some control strategies used in economizer cycles. Such control strategies will be discussed in the airside economizer cycles lesson in Module 2. In this lesson, we are only focusing on the sensor used in such a control loop. We have provided several examples of how temperature can be measured. We have also provided some examples of how moisture content, whether it be relative humidity or the dew point temperature, can be measured. Based off the psychrometric chart, if you know two properties and assume a pressure, you will be able to determine the enthalpy of the air being measured. That is what enthalpy sensors do. They have to perform two such measurements, and then use that information in an internal lookup table or by solving some convoluted equation relating all the properties to provide the enthalpy reading. But you might be wondering, isn't there a dependence on pressure as well? Yes, there is. The psychrometric chart shown here is only for sea level pressure. Some of the more sophisticated sensors, like the ones used to calibrate other sensors, would include a pressure measurement to ensure the reported value of enthalpy was as accurate as possible. But for typical HVAC processes, the level of accuracy is not warranted, thus a constant pressure is assumed, whether that be sea level pressure or some other atmospheric pressure associated with the elevation of the location you are installing such a sensor. Speaking of pressure sensors, let's look at a few different styles. The Bourdon tube is quite common. It is used to measure gauge pressure, which is the difference between the fluid's total pressure and that of the local atmospheric pressure. Such a device works by filling the inside of the Bourdon tube with the fluid whose pressure is being measured. The higher pressure inside the tube will cause it to extend, similar to those blow dragons you see at kids' birthday parties. The extension will cause a mechanical change in the device, such as the positioning of the pointer needle. That position can be used as an indicator of fluid pressure for monitoring purposes, or that mechanical change can be converted to a more usable signal format to be sent back to a controller where the sensor is to be used in a control loop. Such a conversion again would occur in a transmitter. There are many other pressure sensor configurations which incorporate the deflection of some device due to changes in the pressure it is exposed to, in an effort to indicate fluid pressure. There are other devices that measure the change in electrical resistance of a material when stretched. Such stretching can be performed by attaching the material to a component in the pressure gauge, which will deflect when exposed to different fluid pressures. This is very similar to the science behind some of the temperature and relative humidity sensors previously discussed. Now let's talk about flow sensors. Many flow sensors, whether they are used to measure airflow or water flow, fall under the general category of differential pressure flow sensors. Basically, all such flow sensors work off the relationship defined by Bernoulli's equation. It is basically a conservation of energy equation. The total energy at state 1, upstream of the flow sensor, will equal the total energy at state 2, which could be somewhere downstream or in the middle of the sensor. In the equation shown here, the P's are pressures at state 1 and 2. The V's are the velocities at the two locations. The Z's are the elevations of the respective locations. G is the acceleration due to gravity, and rho is the fluid density. When you place a flow sensor in a stream of an incompressible fluid, like the Venturi flow sensors here, the density can be assumed to stay constant, and there would be no change in elevation. Thus, the equation can be simplified to equation 2, shown here. If we assume incompressible flow, the volumetric flow rate between the two states would need to be equal, and thus we can define a relationship between V1 and V2 shown in equation 3. Combining the last two equations and solving for upstream velocity, we can get equation 4, where C in this equation is a constant which will be a function of the sensor design, and more specifically the cross-sectional area at the locations of state 1 and 2. C is defined by equation 5 shown here. Now don't panic if all these equations are new to you. You will not be tested on them. Since equation 4 is the basic working principle for several of the sensors in this category of differential pressure flow sensors, we need to provide a better explanation than what the Montgomery and McDowell text provides. So in essence, we are just measuring the differential pressure between the two locations and solving for the upstream velocity. If it is the volumetric flow rate we are wanting to measure, for example CFM of air or GPM of water, we would just multiply this velocity by the cross-sectional area of the upstream pipe or duct. Orifice plate flow sensors and Venturi flow sensors can be used to measure liquid flow rates, and both work the same way. The difference is just that an orifice plate has an excessive pressure drop for not that much additional accuracy. Thus, it is not often used in HVAC applications. The pitot tube sensor is used to measure the flow rate of a gas, for example air, and it works off the same principle as the Bernoulli equation. Let's multiply all the terms in the equation by the density to put all the units in those of pressure. In a pitot tube, we measure the pressure differential between two locations in the sensor. The two locations are at roughly equal elevations, so the last term on each side of the equation cancels out. The first measurement from the location at the tip of the pitot tube is the total pressure in the stream. Total pressure would equal the static pressure plus that of the velocity pressure, which is the second term in the equation shown. The second location, which has the inlet port orthogonal to the flow stream, will only provide a measurement static pressure. Thus, the only variable left to solve for in the equation shown is velocity, which again could be used to figure out volumetric flow rate. The velocity profiles of flow streams are never consistent across the cross-sectional area. That means if the pitot tube was placed on the edge of a duct, it would measure a different velocity than if it was put in the center of the duct. Therefore, it is not uncommon to place sensors with multiple inlet ports to get a more representative value of the total pressure in the fluid stream. There are also flow sensors which are classified as displacement flow sensors. They are defined in the Montgomery and McDowell text as those sensors that work by using the fluid to rotate or displace a device inserted into the stream. An inline turbine flow sensor has a turbine placed in the flow stream. The faster the flow, the faster it spins. Its revolutions are counted via a variety of methods, and those readings indicate the velocity and/or volumetric flow rate of the fluid stream. Remember earlier when I said we often install sensors to prove flow is actually occurring? The example we gave was the fact that we need to ensure that chilled water is flowing through the evaporator barrel of a chiller before the chiller's compressor turns on. Devices that are often used to prove such flow would also be classified as displacement flow sensors. A paddle flow switch can be used in a water system. When flow occurs, the paddle will be displaced by the flow of the water and subsequently close a switch. That switch will close an electrical circuit, which could then send a signal to the chiller's controller that flow has indeed been proven. The same configuration of a sensor can be used in an air system, but such a switch is often then referred to as a sail switch. All the flow sensors we've discussed thus far require installing junk into the flow stream path. That junk creates frictional losses, which results in the pump or fan having to work harder and burn more energy. There are some options of flow sensors available that can take away such obstructions from the flow stream. These are termed passive flow sensors. Some options we have there are the ultrasonic flow sensor, the Doppler effect sensor, and the magnetic flow sensors. We will not go into the science behind these, but you do see them at times in HVAC systems. Alright, that brings us to the end of our lesson. Again, you don't have to understand how each style of sensor works to be able to understand how HVAC systems are to be controlled. Trust me, you can become proficient at troubleshooting HVAC systems to ensure our systems are operating in the most efficient manner without knowing the calibration process for a lithium chloride dew point sensor. But by providing a few explanations of the more common sensors encountered in HVAC systems, we hope you have gained a better appreciation for what the sensors are trying to do and the difficulties they have in doing them. Attaining extremely accurate measurements are not cheap, and at times not always possible with the available technology. But the good thing is that it is not always necessary for HVAC systems either. Weighing the pros and cons in regards to accuracy, range, reliability, precision, and cost of the various sensor technologies is the responsibility of the controls engineer. Most likely that is not you, but if you are working in engineering flight or the EMCS shop, you do have a say in what types of sensors you want installed on your base. So don't shy away from understanding these devices on a deeper level than we can afford to go into during this course. Again, the lesson objective for this lesson was for students to comprehend the functions of sensors and the obstacles they face in trying to carry out those functions. The corresponding samples of behavior were: state the functions sensors perform in an HVAC control system. Explain the difference between accuracy and precision. Describe when a sensor would require an accompanying transmitter. Recall the selection criteria for sensors. Summarize why relative humidity is not the most appropriate measure of humidity. And discuss why the use of passive flow sensors can benefit the energy performance of a system.